Ani ko ako wala lele. Ubusigan dito, ubusigan ko kang tindahan na ramawaan. Yung tali video. Pero nagparli ko niya, it's now ano yun. Sometimes ko na dito. Hindi ka tigil, hindi ka dito sa magpalan. Hindi ka tigil. Hindi ka talan, tigil siya hindi ka dito sa tigil ko pero hindi ka tigil sa absolutely right. Bahal ni Ventura ka? Ang defense dollar level na, bahal ni.
All right, we'll start the content of week 7 today. And meanwhile, like while I'm starting my screen, if you have any questions, doubts regarding the last week's content, you can ask me. Uh,
Recording in progress.
I hope my screen is one second. Okay, so I think it's okay. Yes, it's week 7. Anyway, okay. So in this week's content, there is your quality of service. By quality of service, it means like how to ensure the internet traffic that we're getting on your systems is well maintained, and how all these traffics are reaching to your system in a high quality manner, and which is what is the priority, what is the protocol, and all these things. Um, I'll ask like if anyone of you like went through the videos or anything. If I have any doubt, you can ask me now. But I'll start with the quality of service lecture. Okay. So in network, we have something called congestion. Okay. That means, let's say this is your Google's server, and this is your computer, and you are requesting some file, Google homepage or Gmail from Google server. So it's coming to your this is your home, and this is your computer. But in between your home and Google's home, there are some other traffic, other network routes as well. So when a packet comes through all these things, it might be working fine here, it might be working fine here, but this part might get congested, and your packet might downfall or experience a downtime here. So this is the congestion that we discussed in the last week's video. That is TCP congestion. There are like the TCP protocol ensures that the congestion control, the TCP congestion control ensures that no congestion in the network. So it will first sense the congestion. If there is a congestion, it will stop sending packet to the network. So how does this congestion actually impacts your network performance? So if there is a congestion, there will be drop in bandwidth. So bandwidth will drop. Bandwidth in the speed, you can say speed of internet. Okay, bandwidth will drop. Then delay will increase. I mean the time required for your packet to reach your served machine, or you can say the download speed will decrease. Then the jitter will increase, because jitter is something like a noise sort of. So if you're like if you're on a phone call with a friend, so if it is a straight line, if there is a noise in between, you hear some muffled voice, and voice with a bit of noise. So these two will increase if there is congestion. The final point is your loss. So what happens is that loss will is increased. So when you are sending packet through a network and if the network is, so if there is router in the network, okay. So if there is congestion in the network, the packet will come here and it will be dropped because of the congestion. So there are things like that. Congestion uh, causes mm, the amount of data that can be transmitted over a link within a fixed amount of time is the rate of the your network traffic. I mean the rate at which you can send is the bandwidth of your uh, network is called the what is bandwidth is like, what is the amount of data that can be transmitted over a link within a fixed amount of time. Uh, um, so some application in the network are bandwidth hungry. Like, so if you are streaming a video, so you must have noticed that earlier as well. If you are just browsing your web page, it will not be consuming much internet. But if you are streaming a live video, or like streaming any pre-recorded video in a very high definition format like 4K, then it will take away all your bandwidth or all your data. Um, so this is called this is called your this is the network bandwidth. So we define the term bandwidth now. We will define the term delay. So we define the term bandwidth first, then we'll define the term delay. So we'll go in a bit. First is bandwidth. Bandwidth is data can be sent per time. Um, uh, so bandwidth is data per time. Like what is the amount of data that can be transmitted over time? Delay. There are several types of network delays. One is transmission delay, one is propagation delay, one is queuing delay. So I'll uh, brief about all these three things. Let's say this is your server or Google server, Google's server, and this is your router, and this is your computer. Okay, so this is a route where you're getting the packet. This is also a route getting some other packets from somewhere else, and so on. Okay, so when a packet, let's say a packet reach here, there will be packet coming from this side as well, some packets, this side as well. So here there will be a queue. Which packet will be processed first? Okay. So if your packet goes and stand here, this is let's say our packet go stand here. So you have to wait for all these things to clear to get processed by this router. Okay. So this is called queuing delay. This is called QUE QUE UING. Queuing. Sorry. This is called queuing delay. The delay that is incurred when the packet is at the queue. Then this packet is processed by this. So second thing is processing delay. When the packet goes to the router, it processes that packet, corresponding packet, and that is called the processing delay. And the third is Uh, Third is transmission delay. Transmission delay is transmission delay. Transmission delay is like, the rate at which a device put the packet onto the route onto the wire. That's like, let's say here is a router and here is your packet, and it is a, let's say, 1 kb. Okay, so the rate at which, so the time that is needed for this 1 kb of data to go into the wire, okay, it's called transmission delay. Okay, and the fourth is propagation delay. Propagation delay. So the time that required from one point of the node to the next point of the node, time required to travel this distance is called propagation delay. So how to calculate this queuing delay? Queuing delay we cannot calculate because it's just a experimental value, where it will depend on the number of queue and the processing power of the machine that this router have, the chip. Then there is processing delay. It also depend on the router. There is no fixed formula for it. But for transmission delay, we have a formula. In transmission delay, we look at, um, so this is um, the time required for this data to go into the wire. So we look at, so time equals to time transmission. So let me just uh, name it as, one second. Delay transmission is equals to number of data byte by the speed, that is data per second, which is equal to the second. I mean, let's say the link speed, is 8 Mbps and the data is 80 MB video. How long, what is the transmission delay, or how long it will take for the machine to transmit onto the wire? It will be 80 by 8 Mbps, MB. It will cancel each other, it will be 10 seconds. Whereas propagation delay is from this point of the router to this point of the router. So for the time, we have to go for distance by speed. It will be the distance, let's say, is 10 meter, and speed is, let's say, 10 to the power 6 meter per second. It will be 10 to the power minus 6 second. The propagation delay is the time required to propagate through the wire is 10 to the minus 6 seconds. So if you have any doubt on this, you can stop me and we can discuss further. But yeah, this is about the delays as of now, bandwidth and delays. Do you have any doubts? Okay. So we shall move on. Then we'll discuss jitter. Jitter is the variation in the end-to-end delay. So jitter is like okay. So there is chart. I didn't see. No, sir. Jitter is like, let's say your packet is streaming like this. These are packets on your network, and let's say there's a congestion in the network, and your packet now looks like this. So if you notice these two things, there is a jitter. Like there is a uneven. It is called variation in end-to-end delay. Like there is an uneven delay in between different packets. So what this does is that in terms of while doing the video streaming, this video streaming um, I mean, if you're streaming a video and there is delay between everything, so your video will frozen. So this is not good for your live streaming sort of application. So this is jitter. Then loss is that, as I said, the dropping of packets. As I said, like I said here, like the router, if it is highly congested, the network, it will simply drop the packet, which is not good for us. Good for us as well. Loss. So jitter is a yeah. So we're like discussing the QAs in the network perspective, but if we come to an application perspective, like where we're using different applications for doing different tasks, jitter is sorry, this quality of service depends um, on the application as well. Such as if you look at your voice application, if you look at your voice applications, the voice application we require the highest priority. So I note it as application quality of service. So the voice has the highest priority. Then there is interacting video. So this is the way we should maintain our, this is the way we should maintain our priority. So if a packet belongs to a voice packet, so if someone is talking on a phone, we want the voice to be very clear. Okay. So that's why like we don't want uh, anything to lose in between voice, because it will be very feeble. So voice has the highest priority. After voice, there is interactive video. The reason we prioritize voice because in interactive video there is at least video you can look at. But yeah, so voice is the highest priority. Next is the interactive video, and the third is the streaming video. Like you are streaming something live, or like not live, even if not live, you're streaming something that is coming in a sequential way. And if your quality of the packet, the quality of the service is not ensured, you will receive very bad pictures and videos on the front side. And the final is data. Let's say you're just browsing a website and just downloading a video, then some sort of delay is fine. So when we see we see a packet from this application layer with the um, your application as voice, it will be like let's say um, while queuing in a router, let's say in the queue there are packets from let me show you that on the router's diagram. um, let's say I just complete this. It is interacting video, then streaming video. There is data. So let's say here's a router, and we are getting packets standing in a queue, and this is data, interactive video, and voice. When this voice packet arrives, it will be prioritized to be processed first, then this one, then this to the same priority. Okay. So the quality of service is that the quality of service refers to the capability of a network to provide better service to selected network traffic over various technologies, including the frame relay and asynchronous transfer mode, Ethernet and 802.1 networks. So this is a formal definition. You can go into the slides and look into that. I'm not gonna discuss that. But the primary this QoS parameter is this four thing: bandwidth, jitter, loss, and delay. Let me first go to your assignment question and see which of the things that I have covered. Question big rate loss characteristics. Okay, so question number 2 is covered. Okay, by this lecture, question number 2 is covered. Question number 1 is not covered. Okay, question number 4 is covered. Question number 4 is covered. Yeah, question number 1, 2, and 4 is covered already. I'll cover question number 1 now. So I will not directly tell the answers, but if you based on the concept that is taught, you can solve the question. If you're if you're not able to solve this just by looking at it, you can stop me now. I can explain that thing again. But yeah, so question number 4. Let me solve it first a bit. Then I can tell if it is feasible to solve or not. Uh, Yes. Question of 4 can also be solved. So yeah, question on 2 and 4 is solved. Okay, so which class does this belongs to? Like if you go for a data, it is just offline mode, and if you go for video conferencing, interactive video, and streaming video. Interactive video is real time, but variable bitrate. Streaming video is real time. Non-variable bitrate, I guess. But anyway, we'll move forward to the discussion. I'll catch up with the questions in a while again. So let's just define what is a flow. So each computer, so this will have a lot of ports, and this computer will have an IP address, IP1. There will be another computer here, and there will be a lot of ports. There will be IP2. Okay. So if this port is connected to this port, there is a flow. And this port is connected to this port, is another flow. This flow 1, this flow 2. Okay. Stream of packets from source to destination is called a flow. Source to destination can be machine to machine, process to process, application to application, socket to socket. We just here tell you about the socket to socket. Okay. Like if we're considering it from application to application, it will be different than socket to socket. It will be different than process to process. Different flow requires different level of quality of service. Uh, okay. Um, so there are different type, like the type of flow, like machine to machine, process to process. In network layer, the end-to-end performance, we maintain the QoS both per hop and end-to-end behavior. So end-to-end performance need to be monitored, and end-to-end delay, bandwidth, jitter need to be monitored. And also, why this quality of service is considered the network layer? Um, because the resource reservation, because the network layer bridges end-to-end and per hop connections. And the same thing, like similarly, we can also like look at the application layer based quality of service. But since it was not covered much in the lecture, I will not cover that. Um, uh, so I'll just start with this uh, basic quality of service architecture. So what it is saying is that, let's say there are two flows. So there is a two flow, and let's just write it this as admission control. Admission control. Okay. In the admission control, what you do is that, let's say there are two flows that is maintained between this PC1 and PC2. Okay, and this is your network in between. Okay, so let's say this port wants to start a connection with this port. Okay, so what it will do is that it will just try to check, do I need to admit this flow or not? Admission control means I will be controlling while I'm admissioning. So it will, let's say there is a flow like this between this point. So it's saying that admission control saying is that if the congestion of network without, let's name it as flow new. Okay, without f new is same as the congestion of network with f new, then add, else don't. It's saying, so let's say there are already two flows available on
Coffee tarayla. Oh yeah. Let's play this.
yeah, so let's say there are already two flows available in the network, and you're trying to add a new flow to the network, like you're trying to make a new connection. So this admission control algorithm says that if I add this flow to the network, so let's say if I add this flow to the network, does it increase the congestion, or like add any congestion to the network? Someone is getting unmuted. Please mute yourself. Yeah. So if you are in the network, if you're trying to add a flow to the network, and let's say the congestion after adding your flow is same or even less than or equal to the congestion that was there earlier, then this type of so then you can admit the flow. Like if I want to add, um it's like saying if you want to add anyone else inside a metro or bus, if it is not increasing the congestion, I will add it. Like um, I will not add. If it is not increasing the congestion, I will add it. If it is increasing the congestion, I will not add it now. I will let it. I'll let the passenger wait for the next bus or next when there is a less congestion. So it's like that. If the congestion is not, if by adding a flow um, uh, is increasing the congestion, then don't add the flow. Wait for some time, then add the flow. You must have noticed it while you were so if you're like trying to call a friend or family member, and sometime you hear this voice, all lines are busy, please dial after some time. So this means your the congestion in the network is higher, and the phone company doesn't want you to start a call because they cannot guarantee you the quality they uh, um, usually promise. That's why they don't want to start the connection. The network does not allow new flow if all the network resources are blocked in servicing the existing flow on their QoS requirement. So uh, also there is another thing that is called classification and marking. That classifies the packets based on their application QoS requirement and mark the packet accordingly. Like as I said, there is a priority that goes on in the application QoS, the quality of service. The voice is more the voice is more prioritized than the interactive video, than the streaming video and the data. So if there is a toll, and if there is no space, then data block will be dropped first, because we don't want data. Like we can just resend it, just ask the sender to resend it, because they're just downloading. It can take time, but for live streaming or interactive video, it need to be taken care um, immediately. Then the next is police policing and markdown. The policing and markdown monitor the flow characteristic and take appropriate action based on the flow QoS. It's like this again the same thing like queuing, dropping, and all this traffic shaping, like traffic policing. Uh, Traffic policing, that is, you put them into a queue, you maintain the flow, and all these things. And another thing is scheduling. Uh, so yeah, the first is admission control, where you are not allowing this. Second is classification and marking, where you are classifying the packet as something like classifying the packet as if it is which packet is this. Then you're policing and markdown. In the traffic policing, you schedule. Uh, sorry. Uh, Sorry. In the traffic policing, and you there are two type of traffic policing. One is service level argument. One is traffic policing. An argument or a contract between the customer and the service provider to maintain a QoS of an application. So this is traffic policing. And the next is scheduling. So in scheduling, what we do is that we maintain certain, like there is two algorithm, famous algorithm on this, like leaky bucket and um, sorry, uh, leaky bucket, leaky bucket and traffic policing. Leaky bucket, and there is the second one is wait. Uh, yeah, I forgot the second one, but there is second one. But the one is leaky bucket. We'll discuss the leaky bucket one, and there is scheduling, which comes under the leaky bucket thing. I will discuss that later. Uh, yeah, then there is scheduling based on the priority. So if like as I said, the priority of boys is more, so this will be prioritize first, and then others will be others will be like process. The next is traffic shaping. In traffic shaping, we shape the traffic. Like if the traffic is coming at a, like let's say you are streaming a video and your file is coming. So this is the let's say this is coming in this way. Where is the jitter diagram? This way. So what traffic shaping will do is that it will the traffic shaping, let's say this is traffic shaping. It will put the packet again in the equidistance delay. So this is traffic shaping. Uh, so input traffic is first, yeah, output traffic has a constant packet to reduce the jitter. Okay, so this ends your another material, but let me see which questions are covered. Based on QoS requirement, video conferencing comes under which class of application? I think we have done this already. Traffic scheduling algorithm. I think I said the traffic scheduling algorithm is uh, traffic policing. Uh, Traffic scheduling algorithm. Traffic scheduling. Traffic scheduling. Hmm. Uh, the traffic scheduling one is weighted fair queue, but I think we'll not discuss that algorithm much. Uh, Four, we have discussed what is the role of scheduling in the basic QoS architecture. Uh, I think we have covered that. Uh, which of the following statement is true? TCP is for in elastic traffic, therefore not preferred for real-time video streaming. Elastic traffic, I think we haven't covered that. We'll cover this. Which of the following is true for admission control? It ensures new flows are entered in the network if QoS of all existing flows along with the new flow can be satisfied. Um, um, it creates packets overflow. It ensures the sender is not overwhelming by a receiver sending packet faster than it can consume. It ensures delivery as fast as created by the sender. I think we have covered question number 7 as well. I covered that now. It in differentiated service architecture, what scheduling technique can be used to implement expedited forwarding? I think we haven't covered this. Which are the following true about TCP? TCP send traffic at a constant rate. TCP ensure congestion will never occur in the network. TCP is a physical layer protocol. TCP detect congestion and act according to avoid it. Uh, yep, I think this was covered also as well. Last question, question number 10. Which of the following is true for traffic policing? It is a congestion control mechanism that brings delays in packets. It buffers the packet with rates that are greater than the traffic setting rate. It is a mechanism that monitor the traffic in a network. It causes delay. I think question number 10 I will cover now. Question number 10, 8, 6 are not covered. 10, 8, 6 are not covered, but everything else is covered. Uh, uh, yeah. So I'll try to um, cover that. Okay. We are going forward. I'll just take 5-10 minutes break. We'll meet again after 5-10 minutes. Okay, so we'll do the leaky bucket and token bucket first. Uh, so what is traffic policing like versus traffic shaping? Mhm. This traffic policing, let's say, this traffic shaping. In traffic policing, what you do is that we just stick to this line, like we'll go like this. Sorry. Hmm. This traffic policing and traffic shaping is like this is traffic, this is time, traffic. Just do this. So this is traffic shaping. So what's in traffic safety? Uh, so in the traffic policy, we'll see first the traffic policy will say leaky bucket. Leaky bucket algorithm, and in the leaky bucket algorithm, uh, so let's say this is your bucket. And so they are the packets that are coming. So what happens is that it just get stored as if it is water droplets in a bucket. Okay. It gets stored as if there is a the packet queue, and so uh, this bucket ensures that the traffic that goes out of the bucket goes like like this, like it's leaking the bucket. It's like leaking out the bucket from the bottom. So it is called leaky bucket algorithm. The packet queue works as a bucket, a single server queue with constant service time. So um, like like the speed here might be different. So the speed here which is coming, it might be different. Like S1, the speed with this packet came might be S2, but the speed at which this bucket um, sends out packet will be S. Let's say S bucket. It will be constant. S bucket. Okay. If the bucket overflows, the packets are discarded. So let's say like it just fills up this bucket, all the packet that is coming will be discarded. Okay. The input rates can vary, but the output rate will always be constant. So if you have doubt in this method, you can ask me, because it's an important method, and there's questions um, regarding that as well. Okay, so then there is token bucket algorithm. So incoming packets are first put in the packet queue. So there is a token generation rate, that is R, let's say, and bucket size is, let's say, B. The rate of traffic that is bounded by the token generation rate. So the rate of the traffic will be the minimum of packet rate into time, and the B plus RT. B is the bucket thing, and R into T is the token generation rate, and time T is the time. But B is the bucket size. So I put it like this. Token bucket like this. This is your router. This is you're generating some token, some sort of token. This R is coming. This is tokens, and this is your bucket B. The R is the rate of the generation of tokens, and B is the bucket size, and this is your packets. The usual stream. So this outing rate RT is the token bucket rate for traffic policy. So RT is defined as minimum of the P into T and B plus RT. This is is looking for the lowest one until send packet in that order. The difference between this leaky bucket and token bucket is that a leaky bucket smooth out traffic but does not permit burstiness. So like if like it just smooth out traffic. Like if the speed is in let's say it's like this is the point in time where leaky bucket is implemented. If it is coming at like variable interval, it will always go out in a same interval. So it might be just this variable interval, it will go out on the same interval. And so token bucket smooths out the traffic and also permit burstiness. If there is no incoming packet, tokens are get added in the no token bucket and the burst traffic is permitted to the amount of token accumulated. Both the leaky bucket and the token bucket algorithm can be used for traffic shaping with the addition of payout buffer, a buffer to add some additional delay to the packet that arrived too early. So burstiness, there's use of this term burstiness. STINESS. Burstiness is that, let's say the bucket is empty for a certain time. The bucket is empty for a certain time and suddenly there is a huge number of data that came to the bucket. So it cannot handle that. It will be full and it will drop the packet. But in case of a token bucket here, in token bucket, what happens is that there is a rate at which tokens are generated and calculated here. And there is a rate at which the packets are coming, actual packets are coming. Token is just like, a tag. So you have packet, you have token, and you pass it. There is a packet coming, there's a token, you connect them and then pass it. So if there is no packets here, it's empty, the tokens will be accumulated here in this token bucket. So once there is a huge amount of packet come, they will just attach all these things to a corresponding token. Since the tokens are already collected and accumulated, it will attach all these things and it will maintain the flow again. So it can handle this burstiness, but the leaky bucket cannot handle the burstiness. This is about like the leaky bucket and token bucket. I think there is not much thing that is involved in this thing. So there is next thing is scheduling. Scheduling is a bit big, like it's a very huge topic in itself. So that's why I will not cover scheduling as of now. I was looking through the slide when I took the break, but it's very big. The scheduling is very big. So we had four things, I guess. We covered in the quality of service. We covered admission control. Then there is classification and marking, and we covered policing and markdown. There's traffic shaping, there is scheduling, and there is link specific mechanism. I think we did this traffic shaping, but we'll drop the scheduling part now. Okay, let me see. Traffic shaping we did. Leaky bucket, token bucket. Scheduling is left. Yep. Scheduling is left, and what else is left? I guess scheduling and link specific mechanisms are left. I think there is one question from scheduling. I already answered that in the video, but there is no question from link specific mechanism, so you'll be fine while doing the assignments. So yeah, so this will be all for this week. We'll meet next week. Thank you. You can drop the call if you like.